Okay, so I want to talk a little bit about wave interference. So sometimes we're going to have two waves that are traveling towards one another but occupying the same medium at the same time. So in wave interference, what we're going to find is that the amplitudes are always going to be additive, but we need to take the directionality of those amplitudes into account. So let's just make a note. Amplitudes will be additive, but I'm going to put additive in quotation marks because it depends on the directionality, whether we're going to be adding like we would in this first case versus subtracting like we would in this second case. So wave interference occurs when two pulses, so a pulse would just be a single oscillation, or two periodic waves encounter one another in the same medium at the same time. So I just want to draw for you really quickly up here the difference between a pulse, right? One singular oscillation, this is a pulse, versus a periodic wave. Which would have periodic oscillations just like this. Okay, so periodic wave. In a periodic wave, you're going to see the same cycle repeating itself, so you'll see a uniformity of frequency, and therefore a uniformity of the wavelength. Okay, so either a pulse or a periodic wave could be encountering another pulse or periodic wave in the same medium at the same time, and we refer to that as wave interference. So here I've shown you three different diagrams of different pulses encountering each other in the same medium. So this first diagram right here is something that's known as constructive interference. Constructive interference. And we call this constructive interference because these two waves are going to meet each other in phase, meaning both of them are going to overlap at their crests. So these two waves are meeting in phase, two waves meeting in phase with one another. And in previous videos, I've already distinguished between in phase versus out of phase. So here we have two waves meeting in phase with one another. Thus, amplitudes will add to form the resulting wave. So if I were to try and imagine these two waves meeting each other at the same point in the medium at the same time, if this amplitude is 1 meter and this amplitude is also 1 meter, then the resulting amplitude when these two overlap will be 2 meters. So I'm going to have a resultant wave that looks like this. Let's see if I can keep it to scale. So I'll have to, alright, I'll just go right here. So this would be my resulting wave. So this amplitude should be 2 meters. And that's just at the moment that these two overlap with each other. It will produce this greater displacement at that moment in time. But once these two overlap, they're going to continue to pass right through each other. So this is how they're initially traveling, then they're going to overlap with each other, and then, so this goes to this, and then they're going to just pass right through each other, so it'll look like, just like before, but now they'll be traveling away from each other once they've passed through in the medium. Okay, so at that moment in time, though, that they're overlapping, that amplitude is going to build because we have constructive interference, meaning that these two waves are meeting each other in phase with one another. Okay, the next scenario that I drew for you is something known as destructive interference. And in destructive interference, we have two waves that are meeting out of phase with each other. So here we have a crest, and here we have a trough. So when these overlap, assuming our amplitudes are still 1 meter each, this amplitude is 1 meter, but this amplitude is really -1 meter. So what's going to happen is these are going to end up canceling each other out. So destructive interference is characterized by two waves meeting out of phase with one another. Thus, the amplitudes diminish. In the example that I showed, the amplitude would be 0 when they're overlapping. So in the example shown, the resulting amplitude when these pass through each other will be 0. At that moment in time when they overlap. So this will actually turn into a resulting wave that just looks like, here's our equilibrium line, and here is the two waves overlapping each other, because +1 plus -1 gives you an amplitude of 0. However, once they finish passing through each other, it will turn back into what we saw before, but now we're going to have this wave going away from this wave. Sorry, I ran out of space. Okay. The final one that I have drawn for you is a little bit funky looking. So let's say we have a situation like this where we don't have complete constructive interference and we don't have complete destructive interference. We have these two pulses that look very different from each other. Again, the resulting wave is going to be additive for these amplitudes. So actually, when these two waves overlap, it's going to produce something that looks like this in the medium. Okay, so this is just some basic wave interference, and now I want to talk to you a little bit about superposition. So I have this worksheet that hopefully you can see pretty well. Okay, so superposition is when two waves occupy the same medium at the same time, their displacements add up on a point-by-point basis. So that's how we're going to define it, and I'm going to just bring this here so you can actually see the worksheet really quickly and maybe get a screenshot, and then I'm going to show you how to do it. So wave superposition, here we have two periodic waves, and these are going to meet in the same medium at the same time, and we want to figure out what does the resulting wave look like in that medium. So the way we're going to do this is we're going to go line by line. So I'm going to start here and go down this line, and I'm going to add up the amplitudes for waveform A and waveform B at the same point in time on either one of their charts. Well, waveform A has an amplitude of 0 at this first point. Waveform B simultaneously has an amplitude of 0. So 0 plus 0 is going to give us our first point on our resulting wave, which is 0. Okay, so I'm just going to write that right here, 0 plus 0. Okay, now I really want to add some lines to this chart, and I really want to add lines in anywhere that there is a change in directionality. So I'm going to go halfway between this column, like this, and make a little line for myself because I want a point halfway down here. So let's go down position 2. So starting with waveform A, well, if I have numbered this first line a displacement of +1, I can see that at position 2 it's a little bit above 0.5, so I'm going to call it 0.75. Maybe I'm being a little generous there. And then for waveform B, we can see it's at +1, so I'm going to label that +1. So then for our resulting wave, we're going to take 0.75 and add it to +1 to get our resultant displacement on our new waveform. So we're going to get 1.75, so I'm going to plot that point now on my new equilibrium line. Okay. Now I'm going to go to line 3, and I'm going to look at the displacement on waveform A, which appears to be 1. So I'm going to mark that as 1. And then I'm going to go to my displacement on waveform B, which is 0. So 1 plus 0 gives me a resultant displacement of 1. So now I'm going to plot that on my new wave. And I'm going to continue to do the same thing throughout this entire sheet. So if I go halfway down this next column, I'm going to see the same thing about 0.75. So 0.75. If I go down to, so here's row 4. If I go down to waveform B, the displacement is now -1. So my resultant wave is going to be 0.75 minus 1. So that's going to give me a -0.25. And now I'm going to plot that right here. Okay, so you're going to continue to do this and you will get your resultant waveform. So I'm just going to lift this up. I would like for you to show all your work, but I want you to finish this on your own. And you're going to submit that to this assignment. Okay.